Sebastian obtained his PhD from the University of Leeds in 2017, working with Professor Steve Marsden in synthetic organic chemistry. Then he joined Nick Turner and Sabine Flitsch's for several years, first working on the chemoenzymatic synthesis of chiral amines before focusing on continuous flow biocatalysis. And after a year working with Nigel Scrutton at the Future Biomanufacturing Research Hub, he moved to Keele University to start a lectureship in chemical biology.
Thank you very much for giving me the opportunity today. And yeah, I usually start talks anyway and tell people where Keele University is, because most questions I get when I tell people I work there is, where is Keele? So we are a large campus university, the biggest campus university in the UK. We are situated here in North Staffordshire, about halfway between Birmingham and Manchester. And my pub quiz fact for the day is that we are the only university in the United Kingdom that is named after a village, which is perhaps why nobody has ever heard of us. But I am not here today, obviously, to talk to you about obscure facts for universities in the UK. I'm talking about flow biocatalysis. So there's sort of a lot of reasons to do flow biocatalysis, but I think thinking about the challenges of running standard biocatalytic reactions is probably the place to start. So there's obviously several things that we think about, particularly when coming up to scaling up biocatalytic reactions that are quite challenging. So this includes things like substrate tolerance and productivity being low, and enzymatic stability obviously can lead to quite a few issues when it comes to scaling up biocatalytic reactions. And sort of teeing up the rest of my talk, unproductive enzyme combinations can also be an issue. So putting two enzymes that aren't compatible together in the same pot. So this is where flow can sort of come in and help out here. So we can think that obviously the reaction is continuous, so we get a continuous product removal, which can improve productivity and avoid substrate tolerance problems. And especially with the mobilization, it removes the protein from the reaction mixture, so this can simplify the downstream processing. And also coupled to a mobilization, we can think about compartmentalization, so thinking about discrete sort of reactor modules to avoid these enzyme combinations that can't be obtained when we do these in batch. So I'm going to start talking first about oxidase enzymes. So oxidase is obviously a really attractive class of enzymes, not just for biocatalysis, but for sort of synthetic chemistry in general. You know, a lot of the time they only depend on molecular oxygen as an external cofactor, and they proceed with extremely high selectivities, but that dependence on oxygen can often lead to other issues. So the limitation can be the concentration of oxygen in the aqueous phase due to its solubility being quite low. So its maximum theoretical limitation is about 250 micromolar, which works out at roughly 8 mg per liter. So this can leave oxidase enzymes being quite sluggish when they're operating in batch reactions. So, for example, for some of the engineered galactose oxidase variants, the KMO, the kinetic constant for oxygen, has been estimated to be up to 5 millimolar. So before you've even started your reaction, you're already running well below your optimum for some of these enzymes. So, you know, can flow provide a solution for oxygen limitation? And there's been quite a few examples in the literature of different reactors that have been used to improve oxidase enzymes. So falling film reactors and agitated cell reactors. John Woodley's done quite a lot of work in this space, but a lot of these reactors will just increase the mass transfer and improve the transfer rate of oxygen, and you can never get above that 250 micromolar concentration. So some work this work was done when I was working with Nick and Sabine, a lot of it, and finished off at Keele, but the work we're going to start talking about is with University of Leeds. So this was done in collaboration with Professor John Blacker, Professor Nick Poor, and Dr. Michael Chapman at the Institute of Process Research and Development there. And the work was to basically try and come up with a safe way to circumvent this oxygen limitation and get these super higher levels of oxygen within the aqueous phase. And the way they did this, so Nick and John designed this multi-point injection reactor termed the MPIR. And what this can do is these feeds here generate these pools of hydrogen peroxide in solution. And using catalase, which is an enzyme that quickly degrades peroxide into oxygen and water, you can generate supersaturation of oxygen within your aqueous phase in this reactor and provide above ambient concentrations of oxygen for your enzymes. So in practice, the work was done with galactose oxidase, an engineered variant from Nick's lab, which was engineered to work towards more organic substrates rather than carbohydrates. So in batch, this reaction is rather sluggish, quite slow, and limited by substrate concentration. However, putting this in the MPIR, you can see a much more efficient reaction. So double the substrate concentration, going to near full conversion in only 8 minutes. And the reactor was a 2.6 mil reactor, so it's not a small scale in the sense of a sort of Eppendorf. And the space-time yield for these is much higher. So you can see a marked improvement by using this. And we actually managed to measure that the dissolved oxygen concentration was up to 10 times higher than that compared with ambient aqueous phases. So you can see that that's around 80 mg per liter, and you're really getting up to the point where you're making these enzymes closer to some of the KMOs and in excess of that to avoid that kind of limitation there. So we also showed that this could work on some carbohydrates I'm not going to talk about today, but what we were interested in was the fact that you could generate these quite reactive intermediates. So obviously aldehydes need to be used quite quickly, they can oxidize, and we were looking at different ways that we could sort of use this in a useful way. So Nick's lab published this paper a few years ago, whereby they used this engineered choline oxidase variant to generate aldehydes, and in the same pot, this is all in batch, they took a redam and were able to convert the alcohols in situ all the way through to the substituted amines. So we took the choline oxidase variant and we tried this in the MPIR, and there was a lot more optimization that went into this, but a long story short, we were able to really improve the efficiency of the choline oxidase oxidation using the MPIR. So we did see issues with over-oxidation to the acid using hydrocinamyl alcohol. However, changing the pH and increasing the residence time actually managed to get us to near full conversion for this. So this was a nice demonstration that we could use enzymes other than GOase in the MPIR. So previously, we'd also shown that the redams transferred quite well to flow. There's a couple of papers from our group, from Nick's group, that showed this would work. So we knew that we could take these reactions next. We just weren't sure what effect combining them with the MPIR would have. But pleasingly, we could do it, and it worked really well. So generating the hydrocinnamaldehyde and then combining it with this AD redam, the wild type, we were able to get full conversion from the alcohol to the amine continuously in under an hour's residence time across the two reactors. So we were really pleased with this. We could run this continuously for 8 hours with no drop in activity at all. And our previous work with the redams had shown that when they were immobilized on EZG, they could last for quite a while. But we wanted to try and show the sort of modularity of the flow reactors. So we looked at different aminating enzymes. Obviously, transaminases have been used quite heavily in flow by lots of groups. So we took this the transaminase from Bacillus megaterium and simply switched it out, immobilized an EZG again, and we could do the primary amine synthesis in a similar sort of reaction time, so 50 minutes from start to finish. And that was something we were sort of really excited about. But obviously, there's no real issues with combining these two enzymes because this had been done in the previous paper. So what we looked at next was taking an enzyme that perhaps couldn't work in a batch situation with these aminating enzymes and seeing if this would work in this continuous manner. So we'll go back to the galactose oxidase that we'd shown could work in the MPIR. So GOase is a copper-dependent enzyme, and when you run these reactions in batch, which we did as a control, you get no conversion through to the amine at all. So we assume it's coordination of the amines to the copper center that completely deactivates the GOase. So what we thought as well, making the system a bit more advanced, was could we involve switching valves to make it a sort of truly modular system. So we were able to obviously do the GOase in these systems at 60 millimolar to generate our aldehydes, and then using an actual switching valve and then a retrofitted broken HPLC waste valve, cleverly done by Matty here, who's now at Enzyme as well. We were able to build a system whereby we could choose our starting materials and our aminating columns in the end, and either generate the primary amines or the secondary amines in a continuous manner. And we were able to do a panel of aldehydes, primary amines, and secondary amines. And this is all done continuously, simply switching the starting alcohol into the MPIR, and then directing the flow into the different immobilized enzyme beds depending on the product that we wanted. So this was, it worked really, really well. We got near full conversion for all of these substrates, and 2 or 3 of these cyclopropyl benzylamines have actually never been made before. So what we think this shows is this is a sort of really preliminary way to show that you can access areas of chemical space with these enzymes that it's really hard to get to otherwise. And it's something that we're looking at and excited about to look at in the future as well. We're thinking about other incompatible enzyme combinations, if you'd like. Obviously, we were using transaminases and IREDs in the previous examples, but not using them sequentially. So we wondered if we could generate the amine donors for the REDAMs using the transaminases and then feed them into a REDAM pot. Because obviously, in a single vessel, this probably wouldn't work very well, as the IRED would likely be the carbonyl, both the aldehyde and the carbonyl likely both be substrates for the IRED. So you would more than likely get this alkylated product rather than the carbonyl, the ketone alkylated product that you want here. So this is the sort of workflow, taking either alkyl aldehydes or aryl aldehydes, generating the respective primary amines, and then feeding them into the REDAM module to then generate our substituted amines. And we were able to do this. This did work really quite well. You can see here the first example, it didn't work that well. And this was due to the use of AD REDAM, which we talked about before. So what we then did was screened a panel of metagenomic IREDs. You can read the details of which in these papers here. And we were able to find a couple of these metagenomic IREDs that could use the alkyl amines or the aryl amines. So when I say aryl, I just mean these alkyl aryl amines, the ones with the phenols on, versus butyl amine here. But switching out to these different IREDs found from the panel, we were able to get full conversion, and the residence time for this system was only around 20 minutes. And once again, these reactions will run for continuously at least 4 hours or 8 hours. So really demonstrates the potential of it. But we wanted to also show, excuse me, you know, aldehydes are that stable, and we'd already generated them in situ previously using our MPIR. So, you know, could we do this in a sort of 3-stage system? So we were able to do this with both choline oxidase and with the galactose oxidase as well. So the galactose oxidase system was actually a 6-enzyme system, as it needed the HRP and the catalase as supporting enzymes. But we were able to take the alcohols, oxidize, pass through to form our primary amines, and then use the IREDs to generate our substituted amines. And you can see here that the residence times are relatively low here. So this one is only around 50 minutes to go all the way from alcohol to substituted amine. So we think there's a lot of potential here for generating quite interesting molecules using enzymes that wouldn't be able to be generated otherwise. And it's always nice at the end of a paper to have a natural product synthesis. So this is norbeladine, which is a precursor to several drugs, including this sort of natural product that's used for dementia treatment. So we sort of looked at this in a retrosynthetic point of view, and I identified that you could see a sort of vanillin reductive amination here. So that was what we managed to do. We took vanilla alcohol, oxidized in the MPIR, and then mixed with tyramine here. To then generate the norbeladine in a greater than 90% conversion. And this was quite a nice example because the substrate just crystallized out once the reaction was finished, and you could just obtain it by filtration at the end. So a really nice example to finish the paper with there. So I hope that I've shown you that the flow systems that we've described here are sort of like really can give access to chemical space with enzymes that you can't get otherwise, and that you know, we've got the potential to move into sort of cascades that are quite de novo in terms of what you can do in terms of combining them. So just quick acknowledgements for obviously Nick and Sabine for when I worked in the lab. Ash, Matty, who I said, yeah, he's now at enzyme. He did a lot of this work and yeah, it was fantastic. John, Nick and Mike from Leeds, who provided the MPIR, and Matthew from enzyme, who obviously worked with us and supplied a lot of the material that we mobilised the enzymes on. Thanks to you guys for funding, and thank everybody for listening, and happy to take any questions.
Yeah, thanks so much for the talk. Anya, would you like to take over questions? Actually, sure. I might have a quick
thank you
question.
For that. Yeah, go on.
So,
go ahead, Andrew.
Sorry. So when you increase the oxygen levels so much higher above ambient conditions, does that damage the enzyme that uses oxygen as a cofactor if it's not intended to be around that much oxygen at once?
Yeah, I suppose the amount of time it's in the reactor, we don't see any damage happening to it, if that makes sense, because the residence times are so short. Yeah, but you do, I mean, I think it's a lot of the time it's the interface as well that you see some damage at, and because this was so saturated and there was only a really sort of basic back pressure regulator, you did see bubbles forming in it, but we didn't see any of that. But I think it's just by the virtue of the reactions were so quick, so that it was going. But it would be interesting to look at it, definitely.
Yeah, cool. Thanks.
Yes, I also wanted to ask about the oxidation reaction. So I was curious about the concentrations and whether you consider that as a limitation in oxygen delivery. So the higher concentration you want to achieve, then the higher oxygen solubility you need to achieve in your flow system. So is that a limitation? Do you think that there's a ceiling to the concentration
of oxygen? Yeah, definitely. Like I say, it sort of precipitate bubbles out after you sort of get to the end of the flow channel anyway. But I think it was all done at atmospheric pressure in a way. So obviously you're sort of limited by that. But yeah, it wasn't. I wouldn't say it was a controlled oxygen generation. It was just the peroxide was going in at relatively high concentrations. With some of the examples, it was up at 400 millimolar. So you are generating quite a lot, but yeah, I wouldn't say controlled is not exactly how much is in there. But I think we measured it at around 2.5 millimolar was the highest we actually measured in solution. So
okay, all right, thank you. So I see Don have another question. Is that correct, Don? Or maybe it was just a raised hand from the previous talk.
Oh, sorry. Should I go?
Yeah. So yes, please go ahead, Don.
In the last example, you mentioned that the product precipitated, which facilitated purification. Is in situ precipitation on the cartridge ever a problem?
In this instance, it wasn't. I think we got lucky, to be honest. But we have seen some other examples where, so with the EZG in some of the earlier examples, when the choline oxidase was immobilized on that, it generated the acid in situ, and that's stuck to the column because it's silica based. So in that instance, we thought well, initially the guy doing the work thought he'd lost all of his stuff, but it was just stuck to the column. But obviously with everything running through tubes, if you have issues with precipitation, it's going to become quite apparent quite quickly. So I think with this example, it wasn't until, I don't know how he got lucky, but it was after it came out of the end of it. So
okay, thanks.
And I have another question, if you don't mind. So could you comment a little bit about your experience with immobilizing enzyme for applications in organic solvents? Like how successful have you been to use the HISTAG technology to run the reaction in organic solvents?
So yeah, with the HISTAG stuff, we haven't done as much with the organic solvents. There was some work from Nick's lab, one of the papers that was referenced, where they mobilized the choline oxidase on the EZG, and because of the way it was engineered, you could run it in cyclohexanone, and it worked quite well for that. But that obviously in organic solvents, oxygen has a higher solubility anyway, so I think it was amenable to the enzyme. And the problem is with a lot of the immobilized enzymes is that, you know, if they're nicotinamide dependent, you can't run them without any water, because then obviously you've got no cofactor in there. But people have looked at sticking cofactor onto the actual support as well. It's not something that I've done, but I know that's an option for us. I mean, yeah, with all these, obviously we were looking at cofactor dependency, so we couldn't use pure organic solvents, but it's something we've looked at separately in other examples of the oxidases, and they generally work quite well, the engineered ones.
Mm-hmm.